Okay, so on Friday, we began looking at operators, the connection between observables and operators. So the observable is the primitive is the starting point of our discussion. An observable has a spectrum. In other words, there are possible values you can get when you measure this observable. So an observable is something you can measure. So it has possible answers. And to each answer, there is at least one state in which you are certain of getting that answer. So a state where there is no ambiguity, there is no question, there's nothing probabilistic about the result of that measurement. Out of those states and those numbers, we construct an operator, this animal here. And one good thing about this operator, one useful aspect of it is that if you squeeze it between the ket, the state of your system, and the associated bra, you get out the expectation value of the observable Q when we're in this state. So when there is uncertainty and the result of the measurement is probabilistic, which normally will be the case, for most states will be the case, then this simple algebraic formula we showed last time, I think that's where we finished, that leads to the expectation value of that measurement. So that's one way in which this operator Q is useful. You'll find as we go along that there are many other ways in which this operator Q, which for the moment is going to have a hat to distinguish it from the observable Q, which is a physical, conceptual thing, and the operator, which is just some mathematical fiction, which we're going to get used to. Gradually, the distinction will blur, but I hope when you need to, you can distinguish between the physical thing. So energy is the physical thing, and energy comes with an operator, which at the moment would be called E hat. Oh, well, actually, we did introduce that. So the operator E hat is for historical reasons called H, and of course it is the operator sum over all possible energies of energy. So these are the states of well-defined energy, and these are the corresponding energies, and this is the Hamiltonian. In honor of the Irish mathematician who introduced this into classical physics, the corresponding operator into classical physics. Okay. So I guess you will have, I hope you will recognize from Professor Esler's lectures that if we have given a basis, any old basis, then every operator can be turned into a matrix, because given a basis, we can say, given any state phi, then this will be the sum ai I, can be written as this linear combination of basis vectors. If we use any operator Q on a psi, we're going to get some other animal phi. And we can expand phi. We can say that this is equal to the sum of bi I. And then this becomes Q operating on the sum of aj j, this being summed over j, this being summed over I. All right, that's just substituting in here. And then if I want to find out what bi is, or actually, let's change this to k to make a slightly cleaner job. This is just a dummy index. I can call it anything I like. Let's call it k. If I want to find what bi is, I pick out of this sum over all the bk's. I of course, bra through with I. So I bra through with I, and that leads me to the conclusion that bi, because on this sum, we're going to have an I k here, which is going to be nothing except when k is I. So I get a bi is equal to the sum over j, the sum over I of I operator Q j times aj. Of course, this is a complex number, so when we bra through by I, it doesn't get in the way, because I is a linear function on the kets. So we can write this as the sum over j and I of qij, aj, where qij is by definition the complex number that you get in this way by taking the jth basis vector, operating on it with the operator q, and then taking the dot product, as it were, borrowing through with I. So every operator can be represented by a matrix of complex numbers, and of course any one of these things is called, any one of those numbers is called a matrix element, and a lot of quantum mechanics, a lot of physics revolves around calculating matrix elements. So it's a word that's often used. So it's a matrix made up of matrix elements. These matrix elements are complex numbers. So if, now another point to make is, if the basis I is a basis of the eigenvectors of Q. Now I forgot to, on Friday already I think we saw, I forgot to mention it just now, I think on Friday we saw that these things, well, we defined Q this way, and with this definition, it turned out that Qi is an eigenket of Q, and Qi is an eigenvalue. That was a consequence. So these physically important states are, as a consequence of this definition, these physically important states become eigenkets, eigenvectors of the operator Q, and these become the eigenvalues. So now we can say something different. We can say Q is constructed out of its eigenkets and its eigenvalues in this manner. Whereas previously we had a physical statement that the operator Q was constructed out of the states in which there's no ambiguity as to the measurement and the possible results of the measurement. So if we use the eigenkets Qi as our basis vectors, then this matrix becomes very simple. Then Qij is going to be, of course, I, Q, well, I'm going to put this in as Qi, Qj, but Q on Qj is necessarily Qj times Qj. So this becomes Qj times Qi times Qj, but this is delta Ij, so this becomes Qj times delta Ij. So these matrix elements vanish unless j is equal to I. When j is equal to I, we get the number Qj. In other words, in this basis, Q is represented by a diagonal matrix. In other words, Q is going to look like the matrix of Q, Qij, is going to be Q1, Q2, Q3, all these numbers down the diagonal, and nothing everywhere else. And so on until we're bored. Or run out, more to the point, run out of possible states in which Q has a well-defined value. Okay. As a result of that, if we do, if we take the complex conjugate, no, better not do this. Yeah, all right. No, so the Hermitian adjoint, I think from, I'm going to take it that you remember this from Professor Essler's lectures. The Hermitian adjoint of Qij, of Q, sorry, the matrix Q. Now we've got three things now. It's a bit confusing, isn't it? We've got a physical quantity Q, like the energy. We've got an operator Q hat. And we've got a matrix, which is in one particular set of basis vectors, is representing the operator. So I'm a little bit short of notations. I've got a Q and a Q hat, but I'm tempted to write Qij, which sometimes means the particular complex number that you will find in the ith row and the jth column of the matrix Q. But sometimes we use this notation Qij to imply the matrix that represents Q. Do you see that there's a slight overbooking of notation here, and it's universal in theoretical physics. You can't, well, nobody has a natty way of distinguishing between the matrix and the matrix elements. So let me just write the matrix Q. So the Hermitian adjoint of the matrix Q is Qd dagger, and Q dagger is defined so the ijth element of it is the complex conjugate of the jith element of the matrix Q, right? This means the complex conjugate. So the Hermitian conjugate is you swap rows and columns and you take the complex conjugate. That's what happens with the individual elements. So let's see what happens here. So we can, this property doesn't depend on what basis we look at it in. So let's have a look at it there. So what is this? Qij, so in the basis, in the particular basis of the eigenvectors of Q, what does this statement become? It becomes that Q dagger ij is equal to, we've figured out what Qji is. Qji turned out to be Q up there, I delta ji, or delta ij, it doesn't matter. Right, that's what we found. So that's Qij in this particular basis, and now Ji, I hope I've swapped it over. And now I take the complex conjugate. If Qi is real, then this becomes Qi times delta ij is equal to Qij. So the Hermitian adjoint of Q will be Q itself if it's possible, if all the elements in its spectrum are real. And traditionally, people have said it's obvious that an observable is a real number. And I remember as an undergraduate thinking, hang on a moment, that's ridiculous. The impedance of a circuit, right, is something that I have to measure. You know, it might be something you do in you might have done last year in some of the electronics practicals, measure the impedance of this circuit at this frequency. It's clearly a complex number. So it's nonsense to say that observables have to be real. Of course they don't have to be real. But if they are real, then the observable will be represented by an Hermitian matrix. So if the spectrum is all real, then Q hat is Hermitian. This is in the great majority of treatments, this is all back to front. People say that every observable is going to be represented by or associated with a Hermitian operator. They then use some well-known theorem, which I'm sure you've met, which says that every Hermitian operator has real eigenvalues and orthogonal eigenkets. And then, therefore, they say the eigenkets of these things are orthogonal. That's not the way, actually, the flow of the logic of the flow from the real physical world into the mathematical world works. It's the other way. The real argument is that the eigenstates in which the states in which Q has a well-defined value have to be mutually orthogonal because why? Because Qi, Qj, this complex number is the amplitude to get Qj given Qi. And if you know that the result of the measurement is going to be Qi, this amplitude has to vanish for any Qj not equal to Qi. So this orthogonality comes in as a physical requirement of the way we want to use the theory. Then, if the eigenvalues are all real, if the spectrum, the possible results are all real, then you end up with Hermitian matrices, right? But there's no need to be working with Hermitian matrices if you want to work with the complex impedance as your observable. That's not required. But what you do need is this orthogonality result. That is a consequence of, that's a logical necessity of the way we want to interpret the mathematics. Okay. Now we can, of course, multiply operators together. So something else we can do with operators is we've got two operators, R and Q. We can define this animal by the rule that this multiplied object operating on any state of psi is simply the result of using the operators in the sequence given. That is to say, you use Q on at psi first, which makes you some ket, which you then use R on, etc. And if we choose to look at this, if we ask, well, so what's the matrix of RQ? So what's the matrix of this in some basis, in any basis now? It's going to be I, R, what does this mean? It means RQ, J. And into here, we can stick one of our identity operators, the sum over M of M, right? We saw on Friday that this sum is the identity operator. You can stick an identity operator anywhere into a product, and then this becomes I, R hat, M, M, Q hat, whoops, J. And this now needs a sum over M. And what is that? This is RIM, this is QMJ. So this is just the usual rule for a matrix product. So it's RIM, QMJ. And we will want to know what the Hermitian adjoint of this thing is. We'll want to know what RQ dagger ij is. And so what is that going to be? It's going to be I R hat. Do I want to do this? I think I probably don't. I think probably you've seen this done. I think you've seen this done in the math physics lectures this year. So I think we can just remind you that this is Q hat dagger, R hat dagger, right? When you take the Hermitian adjoint of a product of operators, you reverse the order of the things in the product and dagger the individual bits. And I hope you've seen the demonstration. You'll find the demonstration in the book. If you don't, if you haven't seen you don't recall the demonstration from Professor Essler's lectures. And this is all a bit dry and boring, isn't it? Okay, one thing you may not have seen is functions of operators. So, in particular, for a given example, x, the position x down the x-axis is going to become an operator. And we are going to want to evaluate functions of x like the potential energy at the position x depends upon x and therefore is a function of x. So in classical physics, there is a potential function v of x that tells you the potential energy at the location x. And since x is going to become an operator, v is going to become an operator which is obtained by taking a function of an operator. So we need to know what it means to take a function of an operator. Another example is there's going to be an operator associated with momentum. The kinetic energy of a particle in classical physics is p squared over 2m, the momentum squared over twice the mass, because that's a half mv squared in classical physics. So p squared is a function of p. Very simple one, but it's a function of p. So we need to know what it means to take a function of an operator. When you do statistical mechanics, you will need to, there is a quantity, a density operator, which you calculate the entropy of a system, which involves a logarithm of the density operator, right? So you need to be able to take the logarithm of something. So we need to be able to take functions of operators. So let's decide what this means, right? So what we're going to be done, we're going to imagine we're given f of x. So this is just a boring, at the moment, this is just a boring number. Suppose we're given a function. This is a boring number, and that's a boring number, right? I'm just giving an ordinary function of a complex valued function of a complex valued number, say, right? And let's imagine that we can Taylor expand this. So we can write this as f naught, the value that f takes at naught, plus f1 of x, the first derivative, right? Plus a half f2 x squared over 2 factorial. This is the second derivative plus a third. Sorry, 1 over 3 factorial, a sixth, f3 x cubed, whoops, over 3 factorial, etc. Just so we're going to imagine that our function can be Taylor series expanded. In detail, it might not be possible to expand it around the origin, but then we can expand it around some other place in some little neighborhood. Physicists always assume they can expand their functions, and sometimes that leads to major disasters, right? There are important bits of physics which happen only because you can't actually Taylor series expand everything in life, but it's a good starting point. Okay, so we're given this function. Now we want to know what f of q is, right? What is it? So what is f of q? The answer to that is this. It's the sum of f of qi, qi, qi. So this is the definition. When we say a function of an operator, this is what we mean. So what is it? This here is an operator which has, so it has the same eigenkets as its argument, right? So a function takes an argument, the argument's an operator, this operator has eigenkets. So a function of an operator has the same eigenkets by construction, but the eigenvalues are the given function of the old eigenvalues. And can you see that this is guaranteed to work because we started with a function let's even imagine this was a real valued function of a real valued function on the real variable. So then this is just going to be some real number. For every I, this will be some real number. So this is a perfectly well-defined thing. But actually, it would all work perfectly fine with complex numbers, complex valued functions of a complex argument. So this is what we mean by a function of an operator. It's a problem. I mean, I'm leaving it as a problem. You can now show. So on some problem set, it's a problem to show that this definition is the same as f of q is equal to f naught times the identity plus f1 times q plus f2 over 2 q times q plus, right? So if you've got the Taylor series expansion, then you know what this stuff means, right? Because we know what it is to multiply an operator on itself. We may not know what it is to take the logarithm of an operator, but we do know what it is to multiply an operator on itself as many times as you jolly well want, because we've defined multiplication of operators. So this right-hand side has a well-defined meaning. And you should, and it's an exercise to prove, it's not desperately difficult, to prove that this animal on the right that we're defining here has as eigenvectors these animals, and as eigenvalues these animals, and therefore these two definitions coincide. But this is the more general definition, because this doesn't assume that we can do any Taylor series expanding. This does. But when you can do a Taylor series expansion, or somehow express f in terms of algebra which has meaning for operators, which is just to allow, which is to say only multiplication. For example, you can't divide one operator by another operator. That doesn't necessarily mean anything. But you can multiply them together. So when this definition works, then this one is the same as this one, and that's an exercise that I would encourage you to do. But we'll not take time to do it now. Because we're setting up this mathematical apparatus, and I'm sure you're all dying to do a bit of physics, and I am too. But we do have to cover a couple of little things here. Commutators. Oh, actually, perhaps we should, it's time I moved over here. Okay, so in some sense, the big news with operators is that A hat, B hat is not necessarily equal to B hat, A hat. You know this already in as much as you know that matrix multiplication doesn't commute generally. So when you're multiplying matrices together, you don't expect the product this way and the product that way to agree. And we've agreed that operators, once we take a particular basis vector, system of basis vectors, can be represented by matrices, so it's not surprising that there is this non-commutability. And the elementary texts claim this is the key thing about quantum mechanics. I claim this is not the key thing about quantum mechanics. Non-commuting things occur also in classical physics, and we'll see that concretely as we go down the line. However, it is a fact that these operators do not commute, and we spend a great deal of time calculating this animal, which is AB minus BA. Okay, so the definition of A and B, A comma B in a square bracket, is that it means just this. Now, we have some obvious results. We have that A comma B plus C, the commutator of A with B and C, the result of adding B to C, is clearly the sum. From this definition, it follows that it is just this sum. Oh, yeah. We have this obvious result that AB is equal to BA plus A comma B. One of the reasons why we need to know the value, as you will see, why we need to know the value of a commutator is because we often need to swap, we often need to, want to, whatever. We often want to swap the order in which operators occur around, and the way to do it is to write that AB is BA plus this commutator, which is obviously true. The way I think of it is this adds in the thing that I should have had and takes away the thing that I've put in that I'm not entitled to have. But it's obvious, right? And now, finally, a less obvious result, which is that AB, the product AB, commuted with C, is equal to A comma C with B standing by on the outside of the commutator plus, plus A with C comma B like this. It's easy to prove this. I encourage you to prove it. I'm not going to take time to do it. All you have to do is write down what this is from that definition, and then insert two extra terms which cancel each other, and you'll find you can arrange it like this. It should be B comma C. You're absolutely right. Thank you very much for that. The other one I got right. Yep. Okay, so what is this analogous to? This is analogous to d by dc of AB. If I have to do a differential of a product with respect to C, then that is equal to dA by dC B plus A dB by dC. Right? This is the rule for differentiating a product. And can you see the mirror there? The idea is that taking the commutator of something with C is analogous to taking the derivative of something with C. And this is no accident. This, for a mathematician, in certain contexts, is called a Lie derivative. And the rule that we are familiar with here is that you first of all, if you have a product, you can get the result by having this operation happen on the first thing while the second stands idly by, and then you let the first one stand idly by, and then you work on the second one. So here we have, you work on the first one, second standing idly by, and then you work on the second one with the first one standing idly by. The only material difference between these formulae is that this formula is left invariant if I move B over here, or if I move A over there, or whatever. If I change the order here, it won't make any difference, because these are ordinary boring multiplications of complex numbers. But here it does make a difference. This A comma C is an operator. It's the difference of two operators, so it's an operator. And therefore, it isn't clear that I can swap the order of this operator, and the order in which you write those things down is important. So these rules should be kind of, you should make sure you understand where they come from. You should memorize them. And broadly speaking, once you've got these three rules on board, you never need to look inside a commutator and use this relationship here. It's bad practice, by and large, when you're doing computations, to expand commutators to see what's inside them. In the same way, I would say, as this rule here, of course, comes from looking at AB evaluated at C plus delta C minus AB evaluated at C, all over delta C, limit, all this stuff. You know, using this stuff, you can prove this. But once you've got the rules of calculus, you don't do this expanding stuff anymore. You know, that's what lies underneath it. That's the justification. But you don't go back to that every time you have to do a calculation. Every time you have to differentiate d by dx of x cubed, you do not write that this is x plus delta x cubed minus x cubed all over delta x cubed and come to the conclusion that it's about 3x squared, do you? So please don't resist the temptation to expand out a commutator, to write the contents of a commutator out. There are times when ultimately you have to do that, but most of the time you don't, and try and avoid doing it by using these rules here. Okay. Okay, I'm going to need one result which combines these statements and those statements. We're going to need very shortly to calculate what f of b comma a is. So I will want the commutator. Concretely, this is going to be v of x, and I'm going to want to take the commutator with the momentum operator. And these all need hats, I suppose, yeah. And those things up there needed hats, but okay, you imagine them on. So this is, I'm going to want to calculate something like this. So let's see what this comes to. In order to see what it comes to, I'm going to imagine that I can expand f in this manner. So I can write this as f naught times the identity plus f1 times b plus f2 over 2 times b squared plus blah, blah, right? The Taylor series expansion of f around the origin commuted with a. So now I can use that second rule there, to do the commutator of this product. This is a boring number, right? This is a number. Oh, and this is the identity operator. Sorry, this isn't a number. That's a number, but this is the identity operator. And the identity operator obviously commutes with everybody, because I times a is going to be a, same as a times I is going to be a. So the commutator. So I use the second rule to say that the commutator of this sum with a is the sum of the commutators of this thing with a, vanishes, and this thing with a. So that's going to be f1 b hat comma a hat. This comes outside the commutator. So maybe I should have added that to the rule list there because it's a boring number. But I think it's kind of an obvious principle. Plus f2 over 2 factorial of b hat squared comma a plus f3 over 3 factorial b hat cubed comma a plus, right, till you're bored. So that's the middle rule used. Now we use the last rule to say that this is f1, well, this is just a repeat. But this b squared is b times b. So I can expand this into f2, into b hat comma a hat, b hat, plus, right? So it was b commuted with a. So I worked on the first b while the second b stood idly by. And now I have to put down the first b standing idly by and have the second b worked on by a. Plus dot, dot, dot. Plus f3, etc., right? Which is going to involve 3 terms because it'll be b commuted with a. So there'll be 3 things to consider. And this is as far as I can go in general. But in an important case, if b hat a hat commutes with B, so if this commutator, so B hat, A hat commutator is an operator because it's the difference of two operators. So if this operator commutes with B hat, then this B comma A and this B comma A and this one could all be taken outside, and I have that, so under this condition, that F of B hat commuted with A hat is equal to B hat comma A hat times F1 plus F2 plus, and you see it'll be F3 over 2, because the F3 would have been over 3 factorial, but we would have had 3 terms. Oh, sorry, this is going to be times B. This is, oh, silly me. This is going to be times B hat. This is going to be times B hat squared plus. So this is what this will all reduce to, which can be more conveniently written as df by dB so this is an operator. Whoops, sorry. Yeah, and it doesn't matter which order I put it in. This is an operator. And that Taylor series is the Taylor series for df by dx. So I can write this stuff here as df by dB. And then here is my B comma A. And I was momentarily panicked about having written this in front of this. But we've agreed that this operator commutes with B. That was the condition under which we were making this further development. And if this thing commutes with B, it commutes with every function of B. In particular, it commutes with df by dB, which is a function of B. So it doesn't matter which order I put this in. So this is a function, which means it has the same eigenkets. So that's a result we're going to want. And there's one other thing that now needs to be discussed, which is the physical implications of A commuting with B. So if A hat comma B hat equals naught, we say commuting observables. Then the mathematicians assure us, we have a theorem, and the theorem is that in this case, there is a complete set of mutual eigenkets. We'll call these mutual eigenkets just I. That is to say, for each and every one of these, it is true that A hat on I is equal to AI I, and simultaneously, B hat on I is equal to some number BI on I. Okay. When two operators commute, there's a theorem that says this. What does that mean for the real physical world? What that says in for the real physical world is there is a complete set of states, these states, in which the result of making a measurement of A is definitely known, and simultaneously the result of making a measurement of B is certainly known. So there is a complete set of states in which there is no ambiguity, there is nothing probabilistic about the result of measuring either of these quantities. It's very important to bear in mind that complete. We're not merely saying that there is a state or 10 states with this property. There are enough states with this property that any state can be written as a linear combination, whatever, GI, of these objects, right? They're complete. That's what completeness means, that any state So there is a complete set of states in which there's absolute certainty. It does not mean that the fact that that there's no uncertainty in the value that B takes implies that there's no uncertainty in the value that A takes. That does not follow from the commuting of A and B, as we will see. It may well be the case that there are states in which B definitely has a value for which A, the outcome of measurement of A, is uncertain. So the result of two observables commuting, their operators commuting, is slightly technical because it involves this complete statement. It is that there is a complete set of states in which the outcomes of the measurements of both observables are certain. Okay, now, if A comma B not equal to 0, what does this mean? All it means is that there is at least one ket such that A comma B. There may be an infinite number of kets such that AB operates on them and produces nothing. But there is one. There is at least one. If you say that these operators don't commute, you're asserting that there is at least one ket where the commutator operating on it doesn't produce nothing. So what does this imply? It implies that there is no complete So it's a very weak and not emotionally striking result that it just isn't a complete set of states in which they both have definite values. There may be a very large number of states in which they do have definite values simultaneously. So it is not a statement that you can't know the value of this simultaneously with the value of that. We'll come across a counterexample next term, I guess, a very important counterexample. So don't run away. It's very, very widely held misconception that if two operators don't commute, you can't know the value of the one and the value of the other. That's just not true. The statement is that there isn't a complete set of states with that nice property. Okay. We've just got time to start on the next really important section, which is about time evolution. Maybe it's time to move over here. Okay, so physics is about prophecy. It's prophecy that works. It's about predicting the future. That's what it's about. And therefore, the core of it is equations of motion. Newtonian mechanics we think of usually as to do with F equals ma. It's making a statement of what the acceleration is. When you can calculate the acceleration and you know the initial position and velocity, you can predict where your missile is going to be at some future time, where your planet's going to be at some future time, and so on, right? That's what it's all about. So at the core of quantum mechanics sits its time evolution equation, and I'm not going to immediately justify this. I'm just going to write it down. It's the time dependent Schrodinger this is the core of the subject. This is where the physics sits, and it's IH bar d psi by dt is equal to h of psi. This is why it's because it appears in this central, crucial, vital equation. The Hamiltonian sits here. That's why the Hamiltonian matters. Right? Its status in life is unique because it uniquely tells you about the future, and that's what physics is about. Okay, and this is the state of any system. So it's completely non-negotiable for a state which purports to describe a real physical object. It has to satisfy this equation. It tells you how the state evolves in time. It's, of course, a very abstract object. At the moment, it won't be telling you much. And at the moment, I can't connect it. We will be connecting it very shortly, but just at the moment, I can't connect this, for most of you, to classical mechanics. Those of you who've did the S7 short option will recognize this perhaps just a little bit as having something to do with Hamilton's equations. But we will, so the justification, the physical justification is that this is the dominant equation will come by and by. But ultimately, there's no way this can be derived from anything you already know. This cannot be derived out of classical physics. Classical physics can be derived out of this, because classical physics provides an approximation to this, right? The assertion is that nature evolves things according to this equation, and whether that's true or not can only be determined by experiment. It's got nothing to do with mathematics, and it cannot be justified on the basis of classical physics ultimately. But if this is a valid statement, it should produce the right Newtonian equations of motion. I will show you that it does produce the right Newtonian equations of motion, because Newtonian mechanics is an approximation to quantum mechanics, right? Okay, now, suppose this is kind of a scary equation, right? Let's try and find some circumstance in which we can solve this, right? So suppose our system has well-defined energy. In other words, the state at psi at time t, well, the state of psi is equal to E, where HE is equal to EE, right? A state of well-defined energy has to be an eigenfunction of the energy operator H with eigenvalue E. That's what it is. So let's suppose that our system happens to have well-defined energy. Then it will have to solve this equation, and we'll have IH bar dE by dt is equal to HE is equal to E. So the rate of change of E is simply proportional to E, and we know how to solve that equation. We spot it just from ordinary old-fashioned calculus. We spot that this implies that E at time t is equal to e to the minus I e t over h bar e of 0. So I feel entitled to write this down on the basis of just boring classical mathematics, which says that if we know that dx by dt, no, I shouldn't do it there. If I know that dx by dt, where x is some variable, is equal to ax, that implies that x of t is equal to x of naught e to the at, right? So this result, familiar result, inspires me to write down that. I can now trivially check by differentiating this right-hand side that it satisfies this differential equation, right? Because when I differentiate this right-hand side, this thing is not a function of time. It's the value that the state of well-defined energy takes at time t equals naught, so it has no time derivative. So the time derivative comes merely from this, which is a totally boring exponential of a bunch of real numbers. Well, apart from the I, all right? So we know how to differentiate this, so it's easy to evaluate the time derivative of this, and it's trivial to check that then E satisfies this equation. So what does this tell us? This is a very important result. It tells us that the time evolution of states of well-defined energy is really dead trivial. They basically don't change. All that happens is their phase goes around, it increments at a constant rate, E over h bar, with a frequency E over h bar, which is, of course, incredibly, for typical systems like this, is incredibly large because h bar is so small and it's on the bottom there, so this frequency is stupendous for an object like that. So this thing has some energy, and its wave function is zooming around at some hysterical rate. That's all that's happening. The beautiful thing is that this enables us to solve the general problem, because if I have a psi I want to solve, so I've got now some system that's not in a state of well-defined energy, and we'll see that real systems never are in states of well-defined energy, but then I can surely write this as a linear combination with coefficients that depend on time of states of well-defined energy. Right? These are a complete set of states because we've been through this. This is just boring, right? So I can I simply put this ansatz, this expression, this expansion into both sides of my time-dependent Schrodinger equation, and we discover that IH bar d psi by dt is equal to IH bar brackets. We have to differentiate this stuff, so it's AN dot ENT plus AN times the time derivative of this times the En by dt. What's that equal to? That's equal to, on this side, h into the sum AN En. I've missed out a sum over n. Indeed, I have. I've missed out a sum over n, thank you, just about here. I'm kind of conscious of that horrible clock. Well, okay, why don't we just write this, carry this on and write this as the sum over n of AN H En. But this term here cancels this term here, IH bar AN. So IH bar den by dt is HEN. So these terms all cancel those terms, leading to the conclusion. So when I look at this stuff is equal to this stuff, I've cancelled this, so the right side now says nothing, and the left side has this stuff, has A dot, so I've got the conclusion that the sum over n of AN dot En of t equals naught, bra through with an EI of t, and that leads to the conclusion that AI dot equals naught. So the AI are constant. So we have a solution. This enables us to write down the solution to the general problem. We have that psi of t is equal to the sum of some constants, AN, which you can determine from the initial conditions, times En of t. But I can explicitly write that out because I know how this thing evolves in time. This is the sum AN of naught e to the minus I En of t, ENT over h bar times En of naught. So so this is this is a fabulously important equation. So this part of it is. It needs to be burnt into the back of the retina, and it's the key to everything, because and what it tells us is once we know what these states of well-defined energy are and the approved energies, we can trivially evolve in time the dynamical state of our system and predict the future. We have everything. That's it. So a huge part of this subject revolves around finding what these states of well-defined energy are, because they have this enormous predictive power. They're miracle, they're sort of wonder drug. They solve the problem. They do it. So we'll talk some more about them tomorrow.